Alright, so to answer this question, let's go through a little exercise here. And we're going to need a fairly big diagram. I'm actually going to even use my ruler. See, I'm going to go with this. And we're just going to look at some curve here. I'm going to make this one easy just for development of this concept. And this curve is f of x. And so I'm going to choose some point P. I'm going to put it down here. There's my point P. And we want to find the tangent to the, or we basically want to find a tangent line here, and we want to find the slope of that tangent line. Now, as of right now, we don't have any method to find the slope of that tangent line. However, we do have the ability to find the slope of a secant line. So what we're going to do is I'm going to go ahead and sketch in a secant line right here. And so we have the secant line, and we'll call it, so I'll put here secant line. And let's find the slope of this secant line. So what is the slope of the secant line? And to remind ourselves, a secant line is a line that intersects a curve at 2 points. So back at a circle, if you go through the circle, that is a secant line. Okay, well, to find the slope of a line, we need 2 points. So let's get those 2 points. So we'll call this point here x. So that means if this is x, and we want the y-coordinate of that, we would just put this into our function f of x. So point P has the point x, comma, f of x. Simple enough. Now we want this point here. So to get this point, we're not just going to call it y or b or something. We're actually going to get a distance here, and this distance from here to here is going to be delta x. So that means this point here is x plus delta x. And so we use delta x just to indicate that we have some distance from our previous x that is away from it. Well, that means this point up here is going to have the coordinates. I'm going to leave a little bit of space. X plus delta x. That's its first coordinate. Then we got to put it into the function. So it would be f of x plus delta x. Good. So let's go back down here, and we know that the slope of a secant line, or the slope of any line, is y2 minus y1 all over x2 minus x1. So we have 2 points. We have point P, which was up here. We had x, comma, f of x. And then we had point, I'll just call this point Q, which was delta x plus delta x and f of x plus delta x, which is x plus delta x, f of x plus delta x. Alright, so let's put all this information into our slope equation for the secant. So the slope for the secant, so we need a y2 and a y1. Now to make this work, I'm going to make this y2. So we're going to have f of x plus delta x minus f of x. And then this is all going to be, so this was y2 and y1, and so this is going to be x2 and x1. So this is going to be x plus delta x minus x. Okay, so let's simplify this. We end up with the slope of the secant line is going to equal f of x plus delta x minus f of x all over, these x's cancel out, so we end up with just delta x. Alright, so this little formula that we created here is based on the idea of this figure that if we have an x and then we decide some distance, whatever it is, delta x, to get to our second point, we would have the slope of the secant line. Now, remember that we're trying to use the slope of this secant line to approximate the slope of a tangent line. Well, if I were to put in the tangent line right now, or at least look at it with my ruler, we would realize that that is not a very good approximation for the slope of this tangent line. And we could probably do a little bit better than that. So why don't we go ahead and instead of having delta x this distance, I'm going to go ahead and make delta x this distance. And I'm going to just bring it a little bit closer. So if we do that and we sketch in our secant line, we're going to notice that, oh wait, that is a lot better. So here's our tangent line. So the slope of this secant line is going to be much closer than the slope of this secant line. But then we think about it and we go, well, wait a second, we can even make this better. So why don't we put in a delta x that's only this big? So again, we have another secant line. Now, obviously, as we keep on getting closer and closer and closer and closer, and we make this delta x smaller and smaller, we'll be getting closer and closer to this tangent line. We can't make delta x 0, because if we go back to the slope of our secant line, if we put a 0 in for delta x, this thing would be undefined. However, what if we did this? What if we kept on getting delta x smaller and smaller and smaller? So that means this other point gets closer and closer and closer and closer and closer. And we keep on getting small or infinitely close to x without actually ever getting x. Or another way to put it is, what if delta x gets infinitely small or almost 0, but not close to 0? Well, we have looked at a concept, or we looked at a mathematical operation that helps us do that. And that is the limit. So what if we were to take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x? So if we were to actually make delta x approach 0, but not actually get to 0, because that's what a limit does, then at some point we should have the slope of the tangent line. Now, just to be careful, this actually is not going to give us the slope. It's going to give us an equation that represents the slope of the curve. So let me write that down. This will give us an equation that represents the slope of the curve. So let's look at an example of how we might use this new idea of taking a limit of that equation.